Light leaves hot, crowded beginnings and keeps going, not because there is anywhere it must arrive, but because space-time itself opens between every crest of the wave. As the scale of the universe grows, each wavelength grows with it, so that what departs blue becomes red, what departs red becomes radio, and what once burned as a white blaze cools into a soft background hum that fills all directions at once. In general, relativity expansion is not wind through a medium, but the quiet change of the metric, a change that lengthens rulers and the distances between their marks at the same time, like a measuring tape that silently stretches while it is being read. A photon does not tire as it travels. Rather, the distance between its crests increases because the stage on which those crests are laid out has expanded, and the amount of that increase encodes a direct and accepted relation. A photon emitted when the universe is half its present scale arrives today with double the wavelength. The simplicity of that relation hides a gentle irony. The swiftest messenger becomes a chronicle of slowness, because the signal that never ceases to move at the same speed marks time by how much it is stretched. Another quiet irony rests in the colour that fades with distance, not because dust eats the light, but because the emptiness between the dust grains decides the hue that finally arrives. A third irony is that the light most ancient in origin now reaches detectors as a cold whisper, the brightest fire cooled into radio. Ancient photons carry a distinct note in this expanding score. When the primordial plasma cools enough for electrons to settle into orbits around protons, the fog thins, scattering drops, and radiation streams freely. Those photons wander still, now stretched to microwaves corresponding to a temperature of about 2.725 degrees above absolute zero, a value traced with precision by instruments tuned to the sky's faintest glow. A lesser-known detail hides in the quiet in every cubic centimetre of space. There are hundreds of such microwave photons, more numerous than the atoms that later assemble into stars and creatures. A reminder that the universe is not empty, even where it seems perfectly blank. These photons do not prefer any direction. Their near uniformity is another record of the early state, and the small ripples imprinted upon them are the seeds from which structure later grows. But here at the level of a single wave, what matters is the steady elongation that time and geometry together create. The same physics that stretches ancient light stretches every signal that crosses cosmological distances, and so a galaxy's spectral lines slide toward longer wavelengths by an amount that directly traces how much the universe has expanded while the photon was in flight. The general lesson is plain and empirical. Redshift tracks the scale of the universe, and the pattern it paints across the sky is compatible with a smooth expansion that has carried on for billions of years. Through all of this, the mathematics remains understated. The equations that govern the scale of the universe tie the rate of expansion to the contents of matter radiation curvature and any uniform energy of the vacuum. They do not choose reasons, they merely relate changes, and from those relations a clean prediction emerges that redshift should follow the size of space itself. Spectra oblige. Lines from hydrogen and oxygen and calcium slip toward longer wavelengths, by amounts that match the growth inferred from other measures. Yet, a careful voice keeps one mystery in view: the physical nature of the uniform energy that currently speeds late expansion is not established, and even if a constant energy of the vacuum proves sufficient to describe observations, its origin and magnitude remain unsettled in fundamental theory. The universe demonstrates that wavelengths lengthen as space grows. Why the background expansion now accelerates awaits a fuller account that does not overreach what observation can claim. The mystery does not cloud the record those photons deliver. It only marks the edge of understanding where equations work and interpretation exercises restraint. In the expanding frame, the idea of motion invites care. A distant galaxy does not need to fire engines to recede. The very coordinates that track co-moving separation show more separation at later times, and the photon that leaves that galaxy accumulates the record each crest frozen apart a little more than the last. Because the speed of light is constant in any small region, the time between crests at a detector grows exactly as distances grow between co-moving points. That is why astronomers read cosmic history from spectra with confidence. The rule stays simple. Even when the background is not, gravity can focus or shear. A beam, gas can absorb a line. Dust can redden a star's light by preference for shorter wavelengths. Yet the cosmological redshift remains as a separate and cumulative effect, born not of local obstacles but of the changing size of space itself. The observables meet in a single picture, and expanding geometry stretches every light wave in proportion to the growth of the scale, and the sky's measured lines echo that enlargement. If the present epoch is calm compared to the first minutes, it is not empty of consequence. In the long run, more and more wavelengths drift beyond the sensitivity of eyes and mirrors, and signals that begin after a certain time in distant galaxies can never arrive, not because they fail to move quickly enough, but because the ocean of space-time keeps swelling between sender and receiver. The afterglow continues to cool its peak, lengthening into ever longer radio bands, a clock that never ticks in steps, but glides downward without sound. The expanding universe turns colour into chronology, and distance into dilution, and in that slow trade the world gains a measure of its own history, written into the light that reaches it. The smooth geometry that all matter inhabits sets the terms, and the photons simply comply. The first lesson is not a story of forces shoving galaxies apart. It is the measured elongation of light that has been travelling for eons, the patient shift of wavelength that marks the growth of everything between source and detector. The universe keeps expanding, the light keeps lengthening, and the record stays legible in every spectrum that arrives from the deep sky, a simple relation repeating in many voices, whispering the same conclusion in hue after hue. The sky holds its distances in the language of redshift, a law first set down in quiet tables of numbers, where positions and spectral lines recorded through glass and silver revealed a pattern too consistent to be a coincidence. As one measured more galaxies, each one showed that the farther its light had travelled, the more its wavelengths had stretched, and this stretching was proportional to distance. This became known as the Hubble-Lemaitre relation, and it described not just the behaviour of individual galaxies, but the nature of the universe itself. It was not that galaxies were flying through a pre-existing space scattering like sparks from a fire. It was that the space between them was increasing, and that increase imprinted itself directly on the light. Every distant spectrum became both a ruler and a clock. The slope of this relation, called the Hubble constant, carries the present rate of expansion, yet even this seemingly straightforward number is subject to the careful ironies of measurement. One irony is that two of the most precise methods to determine it give values that disagree beyond the comfort of their stated uncertainties. Another is that the constant itself is not constant across all time, for, in the early universe, the expansion rate was far greater, and the name only holds meaning when tied to a specific epoch. A third irony lies in the fact that a universe governed by immutable physical laws can still present its observers with results that differ depending on how and where they look. A reminder that clarity often comes layered with complexity. The evidence for the Hubble-Lemaitre law rests not in one class of object, but in many galaxies, quasars, clusters, and the faint echo of the cosmic microwave background all contribute to its confirmation. Each type of source has its own way of serving as a standard ruler or a standard candle, and each carries different systematic challenges, but when their results are plotted against distance, the lines they draw share the same slope within the limits of their uncertainties. The principle that light from more distant objects is more redshifted remains secure, and this principle forms a central pillar of the modern cosmological model. A lesser-known detail in these measurements is the necessity of correcting for the motion of the observer. The Earth turns on its axis, orbits the Sun, and the Sun orbits the centre of the Milky Way, and the Milky Way itself moves with respect to the rest frame defined by the cosmic microwave background. These motions add small shifts to every spectrum, and without removing them, the underlying relation between distance and redshift would be slightly blurred. The act of subtraction is a quiet assertion that the law is not about our movement, but about the growth of space. Once these motions are accounted for, the plot of recession velocity against distance forms a nearly straight line for distant galaxies curving gently when extended to the very early universe, in accordance with the equations of general relativity. Those equations, when applied to a homogeneous and isotropic cosmos, predict exactly such a relation between the rate of expansion and the energy content of the universe, and the match between prediction and observation is one of the reasons this framework remains the consensus description. Yet within this confidence rests a mystery why the expansion rate appears to differ when measured through the cosmic microwave background's imprint compared to when measured directly from nearby galaxies. The disagreement known as the Hubble tension is still unresolved, and whether it points to unaccounted for observational effects or to a gap in the standard model is not yet known. The recognition of the law's universality did not arrive instantly. In the early days, redshifts were measured for only a few galaxies, and distances were uncertain enough that the slope of the line could have been steeper or shallower by large factors. Over decades, refinements in distance measurement brought greater precision using Cepheid variable stars, the brightness of Type Ia supernova surface, brightness fluctuations, and more recently the time delays in gravitationally lensed quasars. Each method builds a ladder of inference linking one class of object to another, and the convergence of these ladders on the same underlying expansion pattern strengthens the conclusion. A gentle analogy helps here if every village along a river measures the drift of floating leaves and finds that those farther downstream have slowed and spread apart more than those nearby. The pattern hints at the widening of the riverbed itself rather than at any coordinated motion of the leaves. So it is with galaxies and the space between them. The universality of the law is reflected not just in its range, but in its independence from direction. Surveys of galaxies in opposite parts of the sky yield the same proportionality, confirming that the expansion is isotropic to within the limits of detection. This uniformity reinforces the cosmological principle, the assumption that the universe is on the largest scales the same in all places and directions. That principle is not an article of faith, but an inference drawn from repeated measurement, and the redshift-distance relation is one of its most persuasive supports. The recognition of this law also marked a turning point in our understanding of time itself. In a static universe, light from distant objects would simply fade with distance, and the age of the cosmos could be indefinite. In an expanding universe, the slope of the Hubble-Lemaitre relation offers a timescale. The inverse of the present expansion rate gives a rough measure of the time since the scale factor was near zero. Refinements to this estimate account for the changing rate of expansion over time, but the conceptual leap remains. The universe has a finite age, and its light has been stretching since its earliest moments. Observing this law today means looking at the combined result of billions of years of cumulative stretching, imprinted on every photon that reaches us from beyond our galaxy. The pattern's endurance is itself a kind of stillness. Galaxies may move locally under mutual gravity, merging or interacting, but when one averages over vast enough distances, the redshift distance law reasserts itself with quiet persistence. It is as though the small eddies of a local motion vanish into the broad current of expansion, and that current is measured not by the motion of any single object but by the geometry that carries them all. In this sense, the law is both simple and profound, simple in its linearity for nearby objects, profound in the depth of history it encodes. Light stretched by expansion is more than a curiosity. It is the record of the universe's own unfolding, a record that requires no special witness and no repeating event, only the persistence of space itself in changing size. It is this persistence that allows astronomers to use the Hubble-Lemaitre law as a bridge between observation and theory, linking the positions and spectra of galaxies to the equations that describe the entire cosmos. The law endures not because it is imposed, but because it emerges naturally from the way light travels in a universe whose scale changes with time. In every distant spectrum the same message is written in different lines, and the quiet regularity of that message continues to speak of a universe that has been stretching all along. The geometry of the universe is not fixed in a rigid frame, but evolves according to equations that bind the curvature of space-time to the matter and energy within it. These relations, known as the Friedmann equations, follow directly from general relativity when applied to a cosmos that is homogeneous and isotropic on the larger scales. In their plainest form, they describe how the scale factor, a function that measures the relative size of the universe at any given time, changes under the influence of matter, radiation, spatial curvature, and any uniform energy of the vacuum. The first equation relates the square of the expansion rate to the total energy density, while the second describes how the acceleration or deceleration of the scale factor depends on the pressure of each component. Matter which exerts negligible pressure on cosmic scales slows the expansion through its gravity. Radiation, with its pressure equal to 1/3 of its energy density, also slows it, but dominates only in the earliest epochs. A uniform energy of the vacuum, by contrast, has a negative pressure equal in magnitude to its energy density, and this drives an acceleration rather than a slowing. The Friedmann equations carry an elegant irony. They speak in the language of curvature and density, yet they can be solved without invoking any direction in space, a reminder that the evolution of the universe is a global property rather than a set of local motions. Another irony is that these equations, which are purely classical in their origin, successfully describe phenomena born of quantum processes in the early universe, even though the bridge between these realms remains incomplete. A third irony lies in the fact that the same mathematical structure can predict universes that collapse, expand forever, or hover at the balance between the two, depending solely on the sum of their contents. One of the most important quantities in this framework is the critical density, the energy density at which the geometry is spatially flat. If the total energy density is greater than this, the geometry is closed like the surface of a sphere. If it is less, the geometry is open like a saddle. If it is equal, the geometry is flat, extending without curvature in any direction. Observations of the cosmic microwave background, baryon acoustic oscillations, and the distribution of galaxies indicate that the universe is very close to flat, with the total energy density matching the critical value within a small margin. This result carries its own quiet mystery, why the density should be so precisely balanced, especially given that any deviation in the early universe would have grown over time unless counteracted by some process such as cosmic inflation. In the context of the Friedmann equations, the present expansion rate, the matter density, the radiation density and the vacuum energy density together determine the history of the scale factor. The mathematics shows that in the earliest moments when radiation density was overwhelming, the scale factor grew rapidly but decelerated strongly. As the universe cooled and matter became dominant, the deceleration lessened but expansion still slowed. only in relatively recent cosmic time did the vacuum energy become dominant, reversing the deceleration into acceleration. This change of sign in the acceleration is written into the equations without any drama, yet it marks one of the most profound shifts in the entire history of the cosmos. A lesser-known detail is that the curvature term in the Friedmann equations behaves differently from matter or radiation. It scales as the inverse square of the scale factor rather than as higher powers. This means that curvature's influence diminishes more slowly than that of matter or radiation, as the universe expands but more quickly than that of a true cosmological constant, which remains fixed. Thus, a universe near the critical density in its early history is likely to remain near it if vacuum energy dominates at late times, an outcome consistent with what observations suggest. Solving these equations for different mixtures of matter, radiation, curvature, and vacuum energy yields a family of possible expansion histories. In one extreme, a high matter density without vacuum energy leads to eventual recollapse. In another, a low matter density without vacuum energy leads to endless but slowing expansion. With a significant cosmological constant, the expansion accelerates indefinitely. The actual observed parameters place our universe in the last category. The Friedmann equations are not merely theoretical constructs. They are tested by comparing their predictions with observations across a range of epochs. The angular scale of fluctuations in the cosmic microwave background, the pattern of baryon acoustic oscillations in galaxy surveys, and the redshift distance relation from Type Ia supernovae all provide constraints that must be satisfied simultaneously. That these independent measures align with a single set of parameters within the Friedmann framework is one of the quiet successes of modern cosmology. The equations also allow the concept of a particle horizon, the greatest comoving distance from which light could have reached an observer since the beginning of the universe, and an event horizon, the maximum comoving distance from which light emitted now can ever reach the observer in the future. These horizons are not barriers in space but in time and geometry, and their existence is another consequence of the way the scale factor evolves. The fact that there are regions of the universe that we can never observe, not because they are hidden behind objects, but because the expansion outpaces the ability of light to bridge the gap, is a truth that arises naturally from these simple equations. There is a quiet elegance in the way the Friedmann equations require so little to describe so much: a statement of the geometry, an inventory of the energy contents, and the assumption of large-scale uniformity. From these, the evolution of the entire observable universe follows, including its fate under different conditions. The geometry in motion that they describe is not an optional feature of the cosmos, but a direct consequence of the same theory that explains the orbits of planets and the bending of light near stars. The difference lies only in the scale and in the patience required to witness its effects. The equations remain indifferent to why the initial conditions are what they are, or why the vacuum energy has the value it does. These remain open questions lying at the edge of the known, and perhaps awaiting insights from physics yet to come. Until then, the geometry continues to change as the contents dictate, and the light from distant objects continues to carry the imprint of that change across billions of years, a record written in the shifting scale of space itself. The Friedmann equations do not promise permanence. They offer only the shape of the road ahead as drawn by the matter and energy already present. In that sense, they are a cosmological weather forecast on a timescale that makes human history vanish into insignificance. Yet their predictions are as steady as the curvature they describe. The expansion continues, the geometry evolves, and the equations hold indifferent to the brevity of the beings who measure them. In the early universe, when the temperature and density were so high that photons scattered constantly from free electrons, space was filled with an opaque plasma of protons, electrons, and light in equilibrium. In such a state, photons could not travel far without being absorbed and re-emitted, and the cosmos glowed uniformly without the possibility of forming images or transmitting information across large distances. As the universe expanded, the temperature fell, and when it cooled to roughly 3,000 degrees Kelvin, a transition occurred. Electrons combined with protons to form neutral hydrogen atoms, greatly reducing the ability of matter to scatter light. This process, called recombination, was not instantaneous, but unfolded over a span of time during which the mean free path of photons increased dramatically. The result was that radiation previously trapped began to stream freely through space, carrying with it a snapshot of the conditions at that moment. This surface of last scattering, now stretched by the expansion to microwave wavelengths, is observed today as the cosmic microwave background, nearly uniform in every direction, but bearing tiny fluctuations in temperature that record the seeds of later structure. One quiet irony is that this moment of liberation for photons also marked the beginning of darkness for the universe's matter. Once radiation decoupled, the cosmos entered a period without luminous sources until the first stars formed hundreds of millions of years later. A second irony is that the temperature at which recombination occurred was far higher than the surface of any star today, yet the resulting light is now so cold that its peak lies in the microwave band. A third irony rests in the fact that this afterglow, which seems so faint now, is still the brightest thing in the universe when measured across the whole sky, outshining the combined light of all stars when integrated over solid angle. The physics of recombination is sensitive to the density of baryonic matter and the presence of helium, which formed earlier through primordial nucleosynthesis. A lesser-known detail is that the helium fraction slightly alters the timing of recombination because helium atoms bind their electrons more tightly and become neutral earlier than hydrogen. The cooling of the universe through this epoch can be described with precision, and models of recombination match the observed spectrum of the cosmic microwave background to high accuracy. In this way, the early opacity of the cosmos leaves an exact fingerprint that has been measured by instruments aboard satellites such as COBE-W-MAP and Planck. These maps reveal temperature fluctuations at the level of tens of millionths of a Kelvin correlated over characteristic angular scales that correspond to the physical size of sound waves in the primordial plasma at the time of last scattering. These acoustic peaks are the frozen remnants of oscillations driven by the interplay between radiation pressure and gravity, and their pattern encodes the geometry and contents of the universe. The near uniformity of the cosmic microwave background supports the assumption of large-scale isotropy, while the specific pattern of its small anisotropies matches the predictions of a universe governed by general relativity and containing both dark matter and dark energy. Yet even here, in one of the most thoroughly studied signals in cosmology, a quiet mystery remains. Certain large-scale anomalies, such as alignments of low multipoles and hemispherical asymmetries, have been observed, and while they may be statistical flukes, they invite careful scrutiny. The act of seeing the cosmic microwave background is an act of looking back in time to an era when the universe was less than 400,000 years old. The photons have travelled across space that has expanded by a factor of over 1,000 since they last interacted with matter. Their wavelengths have been stretched accordingly, and their energies have dropped by the same factor, cooling them to the measured 2.725 Kelvin. In every cubic meter of space today, there are roughly 400 of these photons moving in all directions with a nearly perfect blackbody spectrum. The stillness they suggest is deceptive, for their very existence in this form is the result of a dynamic process, the transition from an ionized to a neutral medium in a universe that was cooling and thinning as it expanded. Another lesser-known detail is that recombination does not produce perfectly neutral hydrogen instantly. there is a residual ionization fraction that persists for some time afterward, allowing a thin veil of scattering to remain. This residual ionization is later erased by the ultraviolet light from the first stars and galaxies in a separate process known as reionization, which leaves its own subtle imprint on the polarization of the cosmic microwave background. The clarity of the afterglow we see today depends on both the sharpness of recombination and the relatively late onset of reionization, and it is a measure of the balance between these epochs that the small-scale anisotropies have survived with such fidelity. The transition at recombination also froze in place the relationship between the density fluctuations in matter and the oscillations in the photon-baryon fluid. Before this time, baryons were tightly coupled to photons, and their motion was dominated by radiation pressure. Afterward, freed from that coupling, baryons fell more readily into the gravitational wells provided by dark matter. In this sense, recombination is both an ending and a beginning, the end of the universe, as an opaque radiation-dominated plasma, and the beginning of a matter-dominated era in which structure could grow. This moment, calculated from first principles and confirmed by direct observation, stands as one of the clearest markers in the entire history of the cosmos. It is a simple physical process on paper, the binding of electrons to nuclei as the temperature falls, but it transforms the universe's behavior in profound ways. It creates the background light that fills every direction, it allows matter to clump and form stars, and it leaves a record so detailed that it can be used to measure the curvature, composition, and age of the universe with remarkable precision. The photons released at recombination will continue to travel indefinitely, their wavelengths growing longer as the universe expands until in the remote future they are stretched beyond any conceivable means of detection. Even then their presence will persist in principle, a diffuse sea of energy diluted almost to nothing but still a witness to the time when hydrogen first became transparent. In this way, the event of recombination is a point in cosmic history that never stops unfolding, because every moment that we look into the microwave sky, we are encountering it again, its light reaching us, after a journey that has lasted nearly the entire age of the universe. The expansion continues to stretch those photons, the geometry continues to evolve according to the Friedmann equations, and the afterglow remains the most ancient light we can ever hope to see, carrying in its faint variations the imprint of a universe just beginning to show the patterns from which all future structure will grow. The cosmic microwave background is not only a relic glow but a detailed map of the universe's earlier structures, its faint mottling a record of minute variations in density and temperature that would one day guide the formation of galaxies and clusters. These fluctuations on the order of 1 part in 100,000 trace the sound waves that once rippled through the hot plasma of photons and baryons before recombination. Driven by the competition between the inward pull of gravity and the outward push of radiation pressure, these oscillations left a series of peaks and troughs in the angular power spectrum of the background, a pattern first hinted at by balloon-borne experiments and later measured with exquisite precision by space-based observatories. The first peak corresponds to regions where the plasma was compressed at the moment of last scattering, the second to regions where it was rarefied, and subsequent peaks to higher harmonics of this oscillatory motion. One soft irony is that what we now see as a static, frozen pattern was once a dynamic symphony of motion, every crest and trough moving at half the speed of light through a medium that no longer exists. Another irony is that the scale of these patterns across the sky, about 1 degree for the first peak, tells us the geometry of the entire universe, a local measurement revealing the global shape. A third irony lies in the fact that the largest structures we see today, superclusters and filaments, hundreds of millions of light-years across, can be traced back to temperature differences in the early universe of less than 100 millionths of a degree. These patterns carry not only the imprint of ordinary matter, but also the invisible scaffolding of dark matter, which began to clump long before recombination because it does not interact with light. While photons and baryons oscillated together in the plasma, dark matter felt only gravity steadily deepening the potential wells into which baryons would later fall. This quiet division of roles allowed dark matter to set the framework for structure, while ordinary matter, temporarily delayed by its coupling to radiation, waited to be released. A lesser-known detail is that the polarization of the cosmic microwave background also contains information about these early oscillations. The Thomson scattering of photons off electrons at last scattering produces a small but measurable polarization signal with patterns that reflect the velocity and density fields of the plasma. Measuring this polarization helps to break degeneracies in cosmological parameters and to test models of the early universe, including those that describe the generation of initial fluctuations. The agreement between the observed power spectrum, both temperature and polarization, and the predictions of the standard cosmological model is one of the strongest pieces of evidence in support of the LCDM framework. It shows that a universe with about 5% ordinary matter, 25% dark matter, and 70% dark energy evolving under general relativity can reproduce the fine details of the sky's oldest light. Yet even in this precision there remains a mystery. The exact mechanism that generated the primordial fluctuations is still unknown. Inflationary models in which a brief period of accelerated expansion stretches quantum fluctuations to cosmic scales provide a natural explanation for their near-scale invariant spectrum and Gaussian statistics, but direct evidence for the specific physics of inflation is lacking. The search for primordial gravitational waves, which would leave a distinctive curl pattern in the polarization of the microwave background, is part of the effort to probe these earliest moments, but so far such a signal has not been confirmed. The cosmic microwave background is thus both a triumph of explanation and a reminder of unanswered questions. It ties together multiple threads, geometry composition, expansion history and initial conditions, yet leaves open the origin of those conditions. In this way, it is like a photograph, whose composition can be analysed in great detail, even if the story of how the scene came to be is still incomplete. Observing the background is also a lesson in looking back through time without moving through space. Every point in the microwave sky corresponds to a line of sight that reaches the surface of the last scattering, and because the universe has no preferred centre, each observer anywhere would see a similar glow. This universality reinforces the principle that the laws and conditions we infer here apply everywhere within the observable cosmos. A further subtlety is that the small-scale anisotropies are damped by photon diffusion, a process known as silk damping, which erases fluctuations below a certain scale by allowing photons to random walk out of overdense regions before recombination. This smoothing effect limits the amount of fine detail in the map and carries information about the density of baryons and the thickness of the surface of last scattering. Another less familiar aspect is the integrated Sachs-Wolf effect, in which the energy of photons is altered by evolving gravitational potentials along their path to us, especially in a universe with accelerating expansion. This adds a slight correlation between the microwave background and the distribution of matter at later times, providing another window into the influence of dark energy. The study of these subtle imprints has turned the background from a simple relic into a precise laboratory for cosmology, one that continues to refine our knowledge with each new generation of instruments. The faint ripples in the map are the scaffolding of all that followed their amplitude and spectrum, determining the pace at which matter could collapse under gravity, and the scale at which the first galaxies could form. Without the initial conditions recorded in the background, the later cosmic web of filaments and voids would have taken on an entirely different character. The photons we detect today left the surface of last scattering with wavelengths 1,000 times shorter than they have now, and they have been stretched by the same factor as the universe itself. They travel unhindered except for occasional deflections by massive structures, a process known as gravitational lensing, which subtly distorts the pattern of anisotropies. This lensing effect, measurable in high-resolution maps, adds another layer of information tracing the growth of structure over cosmic time. It is an irony that such distortions, which at first might seem to obscure the original map, actually enhance our ability to measure the distribution of dark matter between us and the last scattering surface. In the end, the cosmic microwave background is both the first and the oldest image we can take of the universe. It captures a moment when light began to move freely, when matter began to drift into the wells that would shape its future, and when the geometry of space had already been set on a course that observations today still confirm. It is a reminder that the expansion is not just an abstract parameter in an equation, but a process that has left visible marks across the sky marks that will continue to stretch and fade but will never lose their connection to that first release of light. Each photon in the background is a traveller that has carried its story across nearly 14 billion years, its energy diminished, but its message intact, a quiet record of a time when the universe's future was already written in the faint differences between one region and another. In the first minutes after the universe began to expand from a state of extreme temperature and density, the conditions were right for the formation of the lightest atomic nuclei. This brief era, known as Big Bang nucleosynthesis, occurred when the temperature fell from billions of degrees to a few 100 million degrees Kelvin, allowing protons and neutrons to combine through nuclear reactions without being immediately broken apart by the high-energy photons that dominated the radiation-filled cosmos. The process was governed by the balance between the expansion rate, which set the available time, and the nuclear reaction rates, which depended on the density of baryonic matter and the relative abundance of protons and neutrons. At around 1 second after the beginning, the weak nuclear interaction froze out, locking in a neutron-to-proton ratio of roughly 1 to 6. Free neutrons decay with a half-life of about 10 minutes, so as the universe cooled further, many of them disappeared, but some were captured into helium nuclei before they could decay. By the time nucleosynthesis ceased a few minutes later, the composition of the universe was fixed at about 75% hydrogen and 25% helium by mass, with trace amounts of deuterium, helium-3 and lithium-7. One quiet irony is that almost all the helium in the universe was made not in stars but in this first few minutes, long before the first star ever shone. Another irony is that deuterium, which forms readily in nuclear reactions, is so fragile that it could not survive in the early stages. It appeared only when the universe had cooled enough to protect it, making its abundance today a sensitive measure of the density of baryonic matter. A third irony is that lithium-7, though predicted by the same theory, appears in smaller quantities in old stars than expected, a mismatch known as the cosmological lithium problem, which remains an open question despite the otherwise precise agreement between observation and theory. A lesser-known detail of this epoch is that the number of light neutrino species affects the expansion rate, and thus the final abundances of these elements. Measurements of the cosmic microwave background and primordial abundances both indicate that there are 3 types of light neutrinos matching the predictions of particle physics. The success of Big Bang nucleosynthesis in predicting the correct ratios of light elements for a single value of baryon density is one of the strongest pieces of evidence for the hot Big Bang model. It connects nuclear physics measured in laboratories on Earth to the conditions in the early universe with no free parameters beyond those already fixed by observation. The abundances of these light elements have been measured in pristine environments, such as ancient gas clouds, and the outer layers of metal-poor stars where they have been little altered by subsequent stellar processes. Deuterium in particular is a sensitive indicator because it is destroyed in stars and not produced in significant amounts afterward, so its presence today is a relic of the first few minutes. The formation of helium in this early epoch also had important consequences for the later evolution of the cosmos. Because helium atoms are less effective than hydrogen at cooling gas through radiative processes, their abundance influences how quickly the first stars and galaxies could form. Moreover, the free electrons associated with ionized helium contributed to the opacity of the universe before recombination subtly affecting the precise shape of the cosmic microwave background anisotropies. The freeze-out of nuclear reactions after nucleosynthesis occurred because the expansion of the universe outpaced the reaction rates. Once the density of the plasma dropped and the temperature fell below the thresholds for fusion, the process effectively stopped locking in the elemental composition for billions of years. Stars would later alter these abundances, fusing hydrogen into helium and heavier elements, but the primordial proportions set during Big Bang nucleosynthesis remain visible in environments that have escaped significant stellar processing. The temperature during this epoch was so high that matter and radiation were still tightly coupled, yet the physics involved was entirely within the range of known nuclear processes, allowing the predictions to be made with high confidence. This clarity makes the lithium discrepancy all the more intriguing, as it may point either to gaps in our understanding of stellar physics or to subtle effects in the early universe not yet accounted for. The timeline of Big Bang nucleosynthesis is brief on cosmic scales but vast in implication. In less than 20 minutes, the universe transitioned from a plasma of free protons and neutrons to one dominated by hydrogen and helium nuclei, setting the chemical foundation for all subsequent cosmic history. Without this initial production of helium, the first stars would have been different in structure and lifespan, and the synthesis of heavier elements in later generations of stars would have followed another path. The link between the predicted abundances from Big Bang nucleosynthesis and the baryon density inferred from the cosmic microwave background is a triumph of consistency across widely separated epochs. It shows that the same cosmological model can describe both the nuclear processes of the first minutes and the acoustic oscillations of the first few 100,000 years. The quiet precision of this agreement stands in contrast to the uncertainty of other areas in cosmology, reminding us that some chapters of the universe's story are written in lines so clear they have not been erased by time. The light elements forged in this early fireball remain the most ancient chemical signature we can measure, older than any star, planet, or galaxy. Their ratios tell of a universe that was already expanding and cooling, according to the laws of general relativity, their existence confirming that the cosmos was once in a hot, dense state. Even in the far future, when stars have long since burned out and heavier elements have been locked away in remnants, the primordial helium fraction will persist in the cold gas between galaxies, a silent record of the first minutes. It is a reminder that the universe's expansion is not an abstract concept, but a process with tangible outcomes, shaping the very matter from which all later structures formed. The same expansion that stretches the wavelengths of ancient photons also determined the pace at which protons and neutrons could meet and bind, leaving behind a composition that connects us to the earliest measurable moment in cosmic history. Once the universe became transparent to radiation, after recombination matter began to evolve largely under the influence of gravity. Over time, small variations in density first imprinted in the early plasma and recorded in the cosmic microwave background grew into the vast structures that span the observable cosmos. The driving force in this growth was not the ordinary matter of protons and electrons, but dark matter, a form of matter that interacts gravitationally, yet does not emit, absorb, or scatter light. Dark matter began clumping earlier than baryonic matter because it did not feel the drag of radiation pressure, and by the time baryons were freed from the photon bath, dark matter had already formed a network of gravitational wells. Gas fell into these wells, eventually forming the first stars and galaxies. This gradual assembly of matter into sheets, filaments, and nodes is what is known as the cosmic web. One quiet irony is that the most prominent features of the universe's large-scale structure are defined by something we cannot see directly. Another irony is that while the visible galaxies are arranged along the same filaments as dark matter, they account for only a small fraction of the total mass, giving a misleading impression that the universe is mostly made of luminous matter. A third irony lies in the fact that the vast voids between filaments which seem empty are critical to the universe's overall balance of mass and geometry, their near absence of matter influencing how the rest evolves. A lesser-known detail of structure formation is that the collapse of dark matter into halos is hierarchical small structures form, first merging over time into larger ones, a process that leaves behind substructure within halos. This is consistent with simulations based on the LCDM model, which reproduce the observed distribution of galaxies when the correct physics of gas-cooling star formation and feedback is included. The role of dark matter in shaping the cosmos is tested by multiple lines of evidence. The rotation curves of spiral galaxies remain flat at large radii, indicating the presence of mass beyond what is visible. The motions of galaxies within clusters the pattern of gravitational lensing around massive structures, and the detailed shape of the cosmic microwave background power spectrum all point to a matter density far greater than that provided by baryons alone. Moreover, the growth rate of structure over cosmic time as measured through redshift surveys and weak lensing matches the predictions of a universe where about 1/4 of the total energy density is in dark matter. The cosmic web's filaments are hundreds of millions of light-years long, connecting clusters like threads in a vast three-dimensional tapestry. These structures are traced not only by galaxies, but also by intergalactic gas visible through the absorption lines it leaves in the spectra of more distant quasars. This gas enriched with heavy elements from galaxies shows that material flows along the filaments toward the densest regions, feeding star formation and the growth of supermassive black holes. The voids between filaments are not completely empty. They contain a thin haze of ionized gas, often called the warm-hot intergalactic medium, whose presence has been confirmed by X-ray and ultraviolet observations. The existence of such a network arises naturally from the initial conditions set by the early universe. The same tiny fluctuations in density that produced the acoustic peaks in the microwave background grew under gravity into the scaffolding we see today. In a universe with only baryonic matter, radiation pressure before recombination would have erased many of these fluctuations, delaying structure formation. Dark matter immune to such effects preserved the seeds and accelerated their growth. Numerical simulations show this process in detail, evolving billions of particles under gravity to produce a distribution of matter that closely matches the observed large-scale structure. These simulations reveal another lesser-known detail. The densest knots in the cosmic web are themselves not smooth, but contain smaller halos, remnants of earlier mergers. Such substructure can influence the orbits of stars in galaxies and affect the signals we expect from dark matter annihilation or decay. The growth of structure is not uniform across cosmic time. In the early matter-dominated era, gravity slowed the expansion and allowed density contrasts to grow rapidly, as dark energy became more important in recent billions of years, accelerating the expansion, the growth rate slowed, and the larger structures effectively froze in their overall pattern. This shift is visible in the change of galaxy, clustering with redshift, and in the decreased rate at which new massive clusters are forming today. One of the quiet mysteries in this picture is the precise nature of dark matter itself. Its gravitational effects are clear, but its particle properties remain unknown. Candidates range from weakly interacting massive particles to axions and sterile neutrinos, but no direct detection has yet been made despite decades of experiments. The absence of detection has begun to guide theory toward new possibilities, but the large-scale structure remains a robust indicator that whatever dark matter is, it behaves as a cold, collisionless fluid on cosmic scales. The interplay between dark matter and baryons also reveals an irony of perception. We map the universe using light, yet the framework that determines where that light comes from is invisible. Without dark matter, galaxies would be fewer, smaller, and more weakly bound. With it, the universe gains a structure that is both vast and coherent. Observations continue to refine our understanding of this structure. Surveys like the Sloan Digital Sky Survey and the Dark Energy Survey have mapped millions of galaxies, revealing the filamentary patterns with increasing clarity. These observations, combined with gravitational lensing measurements, allow reconstruction of the underlying dark matter distribution, showing how it evolves over time. The match between these reconstructions and theoretical predictions provides strong evidence that the same physics governs the cosmos on scales far beyond direct experimentation. The cosmic web is not static, but participates in a slow migration of matter from less dense to more dense regions, a flow driven by the same gravitational pull that first gathered the seeds of structure. In the far future, accelerated expansion will stretch the filaments and isolate the clusters they connect, freezing the web into a more fragmented form. But for now, its interconnected strands remain a testament to the reach of gravity over billions of years and billions of light years. The universe's visible architecture, the chains of galaxies, the empty voids, the nodes where clusters meet, is a monument to the interaction of dark matter, baryons, and expansion. It is a reminder that the patterns we see are not merely arrangements of stars, but the outcome of a history written in density fluctuations, amplified by time and sculpted by forces we have measured but not fully identified. The web extends beyond what we can observe, its strands continuing into regions forever hidden by the horizon. Yet its visible portion is enough to show the unity of the cosmos, from the smallest early ripples to the grandest present-day structures. In the closing years of the 20th century, astronomers studying distant galaxies expected to find that the expansion of the universe was slowing under the pull of gravity. The reasoning was simple: if all matter attracts, then over billions of years, the accumulated mass of galaxies' gas and dark matter should gradually reduce the rate at which space stretches. To measure this deceleration, two independent teams observed Type Ia supernovae stellar explosions that briefly rival the brightness of an entire galaxy. These events, caused by the thermonuclear disruption of a white dwarf star that has reached a critical mass, have a consistent peak luminosity once certain variations are accounted for. Because their intrinsic brightness is known, their apparent brightness provides a measure of distance, and their redshift indicates how much the universe has expanded since their light was emitted. By combining these measurements across many supernovae at different distances, astronomers could trace the expansion history of the cosmos. The results were unexpected. Distant supernovae appeared dimmer than they would in a universe that was slowing down. This dimming could not be explained by dust or other local effects. Instead, it implied that the rate of expansion had been increasing for billions of years. The discovery of this late-time acceleration was a profound shift in cosmology, requiring a form of energy with repulsive gravitational effects. One quiet irony is that a program designed to measure the deceleration of the universe instead found its acceleration. Another irony is that the tool used to reveal this, the consistent brightness of dying stars, was a measure of stability, yet it uncovered a cosmic change that reshaped the entire model of the universe. A third irony lies in the fact that acceleration, which in everyday life implies the application of a force, here arises from the properties of space itself without any physical pushing or pulling in the conventional sense. The energy responsible for this acceleration is now called dark energy. In the simplest model, it is equivalent to the cosmological constant first introduced by Albert Einstein in his equations of general relativity to allow for a static universe and later discarded when expansion was discovered. A cosmological constant has a constant energy density per unit volume and a negative pressure equal in magnitude to that density. In the Friedmann equations, such a component causes the expansion to accelerate once it dominates over matter. The transition from deceleration to acceleration occurred when the energy density of matter, which decreases as the universe expands, fell below the constant energy density of dark energy. Observations of supernovae, the cosmic microwave background, and large-scale structure now agree that dark energy makes up roughly 70% of the total energy content of the universe. A lesser-known detail of the supernova observations is the careful calibration required to compare nearby and distant events. Differences in metallicity, the chemical composition of the progenitor stars, can subtly affect the peak brightness, and corrections must be applied to account for these effects. Similarly, interstellar dust can redden and dim the light, requiring measurements in multiple wavelengths to separate true cosmological dimming from local absorption. The robustness of the acceleration result comes from the fact that independent methods confirm it. Baryon acoustic oscillations, which provide a standard ruler for measuring cosmic distances, and the integrated Sachs-Wolf effect, which detects changes in photon energy as they cross evolving gravitational potentials, both point to the same conclusion: the universe's expansion is speeding up. The cause of dark energy remains a mystery. If it is truly a cosmological constant, its value is extraordinarily small compared to theoretical expectations. From quantum field theory, a discrepancy known as the cosmological constant problem. Alternatively, dark energy could be a dynamic field whose energy density changes slowly over time, but current observations show no clear deviation from the constant case. Measuring the equation of state parameter, the ratio of pressure to energy density with high precision is one of the main goals of modern cosmology. The current best measurements place it very close to -1, consistent with a cosmological constant. The acceleration has important consequences for the future of the universe. As space expands faster, distant galaxies recede more quickly, and light emitted by them will eventually never reach us. Over time, only the nearest gravitationally bound structures, such as the local group of galaxies, will remain visible, and the rest of the universe will fade beyond detection. In this way, acceleration erases the evidence of its own discovery for future observers. The onset of acceleration also affects the growth of cosmic structure. In the earlier matter-dominated era, density fluctuations could grow rapidly under gravity, but the repulsive effect of dark energy counteracts this growth, slowing the formation of new large-scale structures. Observations of galaxy clustering at different redshifts and measurements of weak gravitational lensing help trace this evolution, providing another way to probe the nature of dark energy. One might expect that the discovery of acceleration would resolve the universe's fate, but it introduces new uncertainties. if dark energy as constant expansion will continue to accelerate indefinitely. If it evolves, the future could hold scenarios ranging from eventual recollapse to ever faster expansion. Without assuming speculative models, the only secure statement is that the universe is currently in a phase where its scale factor is increasing at an increasing rate, and that this has been true for several billion years. Another lesser-known aspect of the supernova measurements is the challenge of identifying events at very high redshift. As redshift increases, the peak of a supernova's light curve shifts into infrared wavelengths, requiring instruments capable of sensitive infrared observations to extend the measurements farther back in time. These distant events probe the era before acceleration began providing a baseline for measuring the change in expansion rate. The careful statistical treatment of these observations is essential, as the conclusions rest on subtle differences in brightness, measured across billions of light years. The discovery of cosmic acceleration stands as one of the most significant empirical findings in modern science, reshaping the standard model of cosmology into its current form, in which dark energy and dark matter dominate over ordinary matter. It is a model built not from a single type of observation, but from the convergence of many supernova galaxy surveys, the microwave background and gravitational lensing. Each provides a different angle on the same phenomenon, and their agreement is the reason the conclusion is widely accepted despite the mystery of its cause. The irony of dark energy is that it is the largest component of the cosmos, yet it is defined entirely by what it does rather than what it is. Its presence is inferred from the geometry and dynamics of the universe, not from any direct detection. The space it fills is everywhere, its influence uniform, yet its physical nature remains hidden. Until its origin is understood, the acceleration it drives will remain both a cornerstone of cosmology and one of its deepest unanswered questions. The universe expands, and the rate of that expansion increases a quiet but relentless change written into the very fabric of space-time. The simplest explanation for the accelerating expansion is to include in the equations of general relativity a term representing a constant energy density of empty space, the cosmological constant. In this interpretation, dark energy does not vary from place to place or from time to time. It exerts the same effect everywhere, always. A cosmological constant has an equation of state in which the pressure is exactly the negative of the energy density, producing a repulsive gravitational effect that causes the expansion rate to accelerate once it dominates over matter. This model, when combined with cold, dark matter and the observed fractions of baryonic matter and radiation, forms the framework known as the lambda cold-dark matter model. It is strikingly successful at matching a wide array of cosmological observations. The cosmic microwave background's temperature fluctuations, the distribution of galaxies, the scale of baryon acoustic oscillations, and the luminosity distances of type Ia supernovae all fit together within this single picture. One quiet irony is that the term for the cosmological constant first entered physics as a way to prevent expansion, then was discarded, and is now reinstated as the simplest explanation for acceleration. Another irony is that the measured value is vastly smaller than naive estimates from quantum field theory, by a factor of about 10 to the power of 120, a discrepancy so large it stands as one of the greatest unsolved problems in physics. A third irony is that while a constant vacuum energy is mathematically the simplest choice, its simplicity hides the fact that we have no understanding of why its value should be what it is. A lesser-known detail of the lambda cold-dark matter model is that it predicts a very specific pattern for the growth of cosmic structure over time, one that can be tested by observing galaxy clustering, weak gravitational lensing, and the abundance of galaxy clusters at different redshifts. So far the data match the predictions within uncertainties, but there are hints of possible small deviations, sometimes referred to as the S8 tension, which could signal new physics or subtle systematic effects. In the lambda cold dark matter framework, the density parameters that describe the fractions of different components, baryons, dark matter radiation, and dark energy, sum to unity in a spatially flat universe. Observations from the cosmic microwave background suggest that the curvature term is consistent with zero, within a small margin of error supporting the idea of flatness. This is significant because the contribution of curvature to the Friedmann equations diminishes differently from matter or dark energy as the universe expands, and the fact that it is so close to zero today would be unlikely without some mechanism in the early universe, such as inflation, to drive it there. Another subtlety in the model is the role of the Hubble constant, the current expansion rate. Measurements from the early universe inferred from the cosmic microwave background, using the lambda cold dark matter model, give a slightly lower value than direct measurements from nearby galaxies using the cosmic distance ladder. This difference, known as the Hubble tension, is a puzzle that could arise from unrecognized errors in one or both methods, or it could point to physics beyond the standard model, such as a small amount of early dark energy that changes the expansion rate before recombination. The lambda cold dark matter model's predictive power lies in its ability to connect observations across time. The same parameters that describe the acoustic peaks in the microwave background also determine the expected distribution of galaxies billions of years later. The model ties the physics of the first few minutes of nuclear synthesis to the growth of structures in the present epoch. This coherence is one reason it remains the standard description, despite the fact that its dominant components, dark matter and dark energy, are still not directly detected in any laboratory experiment. The model also accommodates the concept of cosmic horizons. In a universe with a cosmological constant, there exists an event horizon, a maximum distance from which light emitted now will ever be able to reach an observer in the future. This is a direct consequence of accelerated expansion and means that there are regions of the universe that are causally disconnected from us forever, even though they may exist within the same overall space-time. This event horizon is not a physical boundary but a limit set by the geometry of the universe. A lesser-known implication of a constant dark energy density is that the expansion rate approaches a constant value in the far future, leading to an exponential growth of the scale factor. In such a de Sitter-like universe, the temperature of the cosmic microwave background will continue to drop, and galaxies beyond the local gravitationally bound group will fade from view, their light redshifted beyond detectability. Eventually, even the closest unbound galaxies will recede faster than light relative to us, due to the expansion of space, not because they violate relativity, but because the geometry itself carries them away faster than signals can arrive. Observationally testing the constancy of dark energy's equation of state requires measuring the expansion rate and the growth of structure across a wide range of redshifts. Surveys such as the Dark Energy Survey and the upcoming Vera C. Rubin Observatory's Legacy Survey of Space and Time are designed to map billions of galaxies, providing statistical power to detect even small departures from the constant case. So far, the data remain consistent with an equation of state very close to -1, but each new measurement refines the possible range. The question of whether dark energy is truly constant is not just academic. If it evolves, the ultimate fate of the universe could be different from the endless acceleration predicted by the cosmological constant. If its density decreases with time, acceleration could slow or reverse. If it increases, acceleration could become so extreme that it tears apart all bound structures in a scenario sometimes called the Big Rip. Yet in the absence of evidence for such evolution, the constant model remains the benchmark. The lambda cold dark matter model also has predictive reach into the early universe, where the same parameters influence the rate at which sound waves in the primordial plasma propagated, setting the scale of baryon acoustic oscillations. Measuring this scale at different times provides a geometric check on the model, and so far these measurements agree with the picture from other probes. The quiet strength of the model is that it is overdetermined more observables exist than free parameters, so consistency among them is a powerful test. And yet the model's very success leaves the deepest questions unanswered. We know how much dark energy there is, but not why. We know its effect on the geometry, but not its origin. We can calculate its consequences billions of years into the future, but we cannot explain its tiny value compared to theoretical expectations. In this sense, the lambda cold dark matter model is both a map and a mystery. It charts the expansion with remarkable accuracy, yet the terrain it describes is shaped by forces whose nature we do not yet understand. The expansion continues under the influence of a component that seems featureless and constant, but whose presence dictates the larger scale behavior of the universe. The horizon grows more remote, the galaxies more isolated, and the cosmos moves deeper into the era of dark energy. Long before telescopes could image galaxies across billions of light years, the universe itself had already set a ruler into its structure, one that would persist through cosmic history and become a key observational tool. This ruler is the imprint of baryon acoustic oscillations, sound waves that travelled through the hot plasma of photons and baryons in the first few 100,000 years. These waves were driven by the tug-of-war between gravity, which pulled matter into regions of higher density, and radiation pressure, which pushed it back out. Because photons were tightly coupled to baryons before recombination, these oscillations propagated outward from initial overdensities at nearly half the speed of light, compressing and rarefying the plasma in a rhythmic pattern. When recombination occurred and photons decoupled from baryons, the pressure support vanished and the oscillations froze in place, leaving a preferred separation scale between regions of higher matter density. This scale, about 150 megaparsecs in today's universe, is preserved in the distribution of galaxies and galaxy clusters, a subtle statistical enhancement in the likelihood of finding pairs of galaxies at that separation. One quiet irony is that a process that ended when the universe was only a few 100,000 years old still shapes the large-scale distribution of matter more than 13 billion years later. Another irony is that the pattern is invisible to the naked eye when looking at the sky. It emerges only through the statistical study of millions of galaxies. A third irony is that the preferred scale is not a direct physical structure, but a fossilized echo of motion in a medium that no longer exists. A lesser-known detail is that baryon acoustic oscillations are measured not by identifying specific structures, but by calculating the correlation function of galaxy positions, or the power spectrum of their spatial distribution. The peak in these statistical measures corresponds to the frozen sound horizon at recombination. This sound horizon can also be measured directly from the angular scale of acoustic peaks in the cosmic microwave background, providing a link between early universe physics and the late-time distribution of matter. The agreement between these two measurements is a strong confirmation of the standard cosmological model and its underlying geometry. Because the physical scale of the sound horizon is set by well-understood physics, it acts as a standard ruler. By comparing its observed size at different redshifts to its known physical size, astronomers can measure the expansion history of the universe. Surveys such as the Sloan Digital Sky Survey and the Baryon Oscillation Spectroscopic Survey have mapped the three-dimensional distribution of galaxies with enough detail to detect the baryon acoustic oscillation signal clearly, and newer projects extend these measurements to higher redshifts using galaxies, quasars, and the intergalactic medium traced by the Lyman alpha forest in quasar spectra. These measurements show how the angular diameter distance and the Hubble parameter evolve with time, providing constraints on dark energy and curvature. The imprint of baryon acoustic oscillations is not limited to galaxies. It is also present in the large-scale distribution of matter, as seen through weak gravitational lensing and in the clustering of galaxy clusters. This persistence across different traces demonstrates that the effect is a feature of the underlying matter distribution, not a property of any specific type of object. A further subtlety is that the amplitude of the baryon acoustic oscillation signal in the galaxy distribution depends on the fraction of matter in baryons relative to dark matter. In the early universe, the baryons participated in the oscillations while the dark matter did not so. The contrast between overdense and underdense regions was reduced after recombination, when the two components mixed. This interplay is captured in detailed models and contributes to the precision with which cosmological parameters can be extracted. The baryon acoustic oscillation signal is also remarkably robust to the complexities of galaxy formation, while the detailed distribution of galaxies on small scales depends on astrophysical processes such as star formation feedback from supernovae and the influence of active galactic nuclei. The large-scale clustering pattern retains the original sound horizon feature. This makes baryon acoustic oscillations a reliable tool for cosmology, largely immune to the uncertain physics of galaxy evolution. One might imagine that as the universe evolves and structures grow under gravity, the pristine acoustic pattern would be erased. In fact, nonlinear evolution does smear out the feature, somewhat reducing its contrast, but this can be partially reversed through a technique called reconstruction, which uses the observed distribution of galaxies to infer and undo the large-scale motions that have blurred the signal. With reconstruction, the sharpness of the baryon acoustic oscillation peak is restored, increasing the precision of distance measurements. The consistency of the sound horizon scale across observations is one of the most compelling aspects of modern cosmology. The value inferred from the cosmic microwave background matches that from low redshift galaxy surveys within uncertainties, even though the two measurements come from entirely different physical processes separated by billions of years. This agreement confirms not only the expansion history predicted by the standard model, but also the idea that the large-scale structure grew from the same initial conditions imprinted at recombination. A lesser-known application of baryon acoustic oscillations is in testing models of modified gravity. Because the acoustic scale is set in the early universe and remains fixed in co-moving coordinates, any deviation from the expected relationship between distance and redshift could signal a departure from general relativity on cosmic scales or a time variation in dark energy. So far, measurements align closely with the predictions of general relativity, combined with a cosmological constant, but ongoing surveys aim to push the precision to the level where even small deviations could be detected. The role of baryon acoustic oscillations in cosmology is similar to that of a yardstick built into the fabric of the universe. It is not a human invention, but a feature left over from the physics of the early cosmos, a fixed scale that we can measure against the evolving geometry of space. In this way, it connects the hot plasma of the first few 100,000 years to the cool web of galaxies we see today. It is an irony of perspective that the universe's largest known measurement tool originated in a time when there were no stars, planets, or observers to use it, and yet billions of years later, it provides one of the clearest windows into the history of cosmic expansion. The sound waves that once rippled through the primordial plasma have long since faded, but their frozen echoes remain a silent pattern that speaks of the universe's earliest motions and the steady stretching of space that has carried them to their present scale. As the universe continues to expand, this scale will grow in physical size, but remain constant in comoving coordinates and unchanging signature in a changing cosmos. In the far future, when most galaxies have receded beyond the event horizon, and the visible universe has grown sparse, the baryon acoustic oscillation imprint will still exist in whatever structures remain bound, a faint but persistent reminder of the time when matter and light move together in a single resonant medium. Light travelling across the universe does not follow a perfectly straight, unaltered path. The gravity of matter, both visible and invisible, bends space-time, and as photons move through this curvature, their paths are deflected. This bending of light, called gravitational lensing, occurs on many scales. When the deflection is strong, as in the case of light passing near a massive cluster of galaxies, the result can be multiple images arcs, or even complete Einstein rings. When the deflection is weak, caused by the cumulative effect of many small distortions from the large-scale distribution of matter, the shapes of background galaxies are subtly stretched and sheared. This effect, known as weak gravitational lensing, is not noticeable for any single galaxy, but becomes measurable through the statistical analysis of millions of them. One quiet irony is that weak lensing, which relies on the imperfect shapes of galaxies, uses the very irregularities in their light as a tool to map the otherwise invisible matter that surrounds and connects them. Another irony is that while lensing distorts the image of the distant universe, it provides one of the clearest ways to see the hidden distribution of mass. A third irony is that the matter responsible for most of the lensing dark matter cannot be observed directly, so we see it only by the way it alters the light from things we can see. A lesser-known detail is that weak lensing does not just measure the static distribution of matter. It also traces how that distribution evolves over time, because galaxies at different redshifts are lensed by structures at different epochs. By analysing the lensing signal as a function of redshift, cosmologists can chart the growth of structure and compare it with predictions from the standard model of cosmology. This makes weak lensing a powerful test of both dark matter and dark energy. The bending of light depends on both the geometry of the universe and the way matter clumps under gravity, so measuring it over a wide range of scales and redshifts can reveal whether general relativity holds on cosmic distances. Surveys such as the Dark Energy Survey, the Hypersuprime-Cam Subaru Strategic Program, and the Kilo Degree Survey have already mapped the lensing pattern across large portions of the sky, and upcoming projects like the Vera C. Rubin Observatory's Legacy Survey of Space and Time and the European Space Agency's Euclid mission will expand these measurements dramatically. The maps produced from weak lensing resemble a ghostly view of the cosmic web, showing dense nodes where clusters lie and long filaments of dark matter stretching between them. These maps match well with the distribution of visible galaxies, but they also reveal mass in regions with few or no luminous objects, confirming that much of the universe's structure is invisible, except through its gravitational effects. One subtlety is that measuring weak lensing requires accounting for the way a telescope's optics and Earth's atmosphere blur and distort galaxy images, effects that can mimic or obscure the lensing signal if not corrected. This makes weak lensing one of the most technically demanding observations in cosmology. But when these effects are modelled and removed, the resulting measurements are among the most direct probes of the total matter distribution. The statistical properties of the lensing shear field can be used to estimate parameters such as the matter density and the amplitude of matter clustering. Here too a mild tension has appeared between the values inferred from weak lensing and those inferred from the cosmic microwave background, echoing the pattern seen in the Hubble constant, and raising the possibility that the standard model may need adjustment. However, the differences are small and continued improvements in both measurement and theory are needed before drawing firm conclusions. gravitational lensing also affects the cosmic microwave background itself. As the background photons travel toward us, they are deflected by large-scale structures, slightly blurring the sharp acoustic patterns imprinted at recombination. This lensing of the microwave background can be measured directly, providing an integrated map of the projected matter distribution over most of cosmic history. Such measurements from the Planck satellite and ground-based observatories agree well with those from galaxy lensing surveys, offering another confirmation of the large-scale structure predicted by the lambda cold dark matter model. A lesser-known application of weak lensing is in cross-correlation studies, where the lensing signal is compared with other traces of structure such as galaxy clustering or the distribution of neutral hydrogen. These comparisons help separate the contributions of different components to the total lensing effect and improve constraints on cosmological parameters. They also allow tests for possible departures from general relativity, since modifications to gravity can alter the relationship between the distribution of matter and the curvature it produces. While weak lensing measures the statistical stretching of background galaxies, strong lensing, the rarer, provides more direct and dramatic effects. In strong lensing systems, the mass distribution of the lens can be modeled precisely enough to measure the Hubble constant from time delays between multiple images of a variable source such as a quasar. These time delay measurements are independent of other distance ladder methods and add to the web of cross-checks on the expansion rate. Both strong and weak lensing reinforce the conclusion that dark matter dominates the mass budget of the universe and that its distribution matches the predictions of structure formation in an expanding space-time. The fact that light from objects billions of light-years away carries a record of the invisible matter it encountered along the way is a reminder that the universe's transparency is never complete. Every photon's path is altered, however slightly, by the web of mass it passes through. The accelerating expansion driven by dark energy influences lensing as well, not only by changing the geometry of light paths, but by slowing the growth of structures that produce the lensing. This means that lensing is sensitive to the balance between dark matter's tendency to form clumps and dark energy's tendency to smooth them out by speeding the expansion. Measuring this balance precisely is one of the key goals of modern surveys. The universe is thus mapped twice, once by the light from luminous matter and once by the distortions that light suffers on its journey. The match between these maps is one of the quiet strengths of the standard cosmological model, while the small differences between them may hold clues to new physics. Weak gravitational lensing is not a single snapshot, but a continuous record of the mass distribution from the surface of last scattering to the present. In each faint elongation of a galaxy's image, in each tiny deflection of a photon from the cosmic microwave background, is encoded the story of spacetime's curvature, the spread of invisible matter, and the pace of expansion. Over billions of years, as galaxies drift farther apart under the influence of dark energy, the lensing signal from distant structures will fade just as the structures themselves become harder to see. Yet for now, the bending of light remains one of our most sensitive tools for tracing the shape and content of the universe, revealing the unseen framework on which the visible cosmos is built. When astronomers measure the geometry of the universe, they find it to be very close to spatially flat, meaning that parallel lines would remain parallel over arbitrary distances, and that the sum of the angles in a cosmic scale triangle would be 180 degrees. This result is not trivial because general relativity allows for universes that are positively curved, like the surface of a sphere, or negatively curved like a saddle. The geometry depends on the total energy density relative to the critical density, a value determined by the current expansion rate and the strength of gravity. If the total density is greater than the critical value, the universe is closed. If less, it is open. If equal, it is flat. Observations of the cosmic microwave background, especially the angular scale of its first acoustic peak, provide the most precise measurement of this geometry, and they show that the curvature term is consistent with zero within about 1 part in 100. One quiet irony is that a universe that is flat on the larger scales can still be filled with curved structures locally, from the bending around stars and black holes to the warping caused by galaxy clusters. Another irony is that flatness is not a generic outcome in cosmology. Without a special set of initial conditions, curvature would tend to grow over time, making the observed near flatness today improbable, unless something in the early universe set it that way. A third irony lies in the fact that while flatness makes the universe infinite in spatial extent, if it is exactly zero, the observable universe remains finite in size, bounded by the distance light has travelled since the beginning. A lesser-known detail is that flatness measurements rely on assuming the physics of the early universe is well understood, particularly the sound horizon at recombination. Any change to this physics would alter the inferred curvature. The apparent flatness of the universe is often taken as evidence for a period of cosmic inflation in the very early universe, during which rapid exponential expansion would have smoothed out any initial curvature to near zero. In the standard model, the curvature parameter scales inversely with the square of the scale factor, so as the universe expands, even a small deviation from flatness at early times would have grown to be large today unless suppressed by such a process. Inflation, by increasing the scale factor by an enormous factor in a fraction of a second, makes the observed flatness a natural consequence. Without inflation, the fine-tuning required for the universe to be so close to flat today is extreme. Observationally, the near-flatness result emerges not only from the cosmic microwave background, but also from baryon acoustic oscillations and the distance redshift relation of supernovae, all of which fit comfortably into a flat lambda cold dark matter model. However, the uncertainties in curvature are not exactly zero, leaving open the possibility of a small positive or negative value. Current limits suggest that if the curvature is not exactly zero, the radius of curvature is at least many times larger than the observable universe. This means that any departure from flatness would be imperceptible in everyday cosmic structures and only detectable through precise statistical measurements. The concept of curvature is tied to the geometry of spacetime itself, not to the bending of objects within it. In a flat universe, the rules of Euclidean geometry apply globally, but general relativity still describes the local curvature produced by mass and energy. This distinction can be counterintuitive, as we're used to thinking of curvature in terms of visible bending, yet in cosmology, curvature refers to the shape of the underlying space in which all matter resides. A lesser-known implication of a flat universe is that its future is determined entirely by the balance between matter and dark energy. In a closed universe without dark energy, gravity would eventually halt expansion and cause recollapse. In an open universe without dark energy, expansion would continue forever but slow over time. In a flat universe with a cosmological constant, as we observe, expansion will continue forever and accelerate indefinitely, carrying most galaxies beyond our event horizon in the far future. Measuring curvature with high precision is challenging, because it is degenerate with other cosmological parameters. For example, a small positive curvature can mimic the effect of slightly changing the dark energy equation of state in certain observations. This is why multiple independent probes are needed to break these degeneracies. Combining measurements from the cosmic microwave background, baryon acoustic oscillations, and supernovae reduces the allowed range for curvature and strengthens the case for flatness. One subtlety is that these measurements assume the large-scale homogeneity and isotropy of the universe. If the universe was significantly inhomogeneous on very large scales, It could bias the inferred curvature. So far there is no strong evidence for such departures from the cosmological principle, but they remain a consideration in interpreting results. The near flatness of the universe also places constraints on exotic models of cosmology, such as those involving extra dimensions or varying fundamental constants, since many of these would naturally produce curvature at some level. The fact that we observe such small curvature limits the range of viable alternatives to the standard model. The philosophical implications of flatness are sometimes noted if the universe is spatially infinite, then the observable part is just a tiny patch of an unbounded expanse. Yet infinity is not required if curvature is slightly positive. The universe could be finite but enormous, wrapping around on itself in a way that might in principle allow light to circle it, though in practice the timescales would exceed the age of the universe by many orders of magnitude. In a slightly negative curvature case, the universe would be infinite and open, with geometry resembling a saddle in 3 dimensions, yet still almost indistinguishable from flat over the observable scale. In all these scenarios, the observed near flatness remains one of the most striking features of the cosmos. It ties together early universe physics, the growth of structure, and the ultimate fate of expansion. It suggests that whatever shaped the initial conditions did so in a way that left the global geometry remarkably simple, even as local structures became complex. As we look deeper into space and further back in time, each new measurement of the cosmic microwave background or galaxy clustering refines our view of this geometry, confirming again that the large-scale shape of the universe is within current precision flat. The expansion continues in this nearly flat framework, the horizon steadily receding, the curvature term in the equations remaining vanishingly small. It is a cosmic stage broad, and even on which the play of matter, radiation and dark energy unfolds, without edges or boundaries in sight, yet bounded for us by the limits of light's long journey. In an expanding universe, there are limits to what can be seen, not because of any opaque wall, but because light requires time to travel, and the geometry of space-time imposes boundaries on what can ever be observed. 2 such limits are especially important in cosmology: the particle horizon and the event horizon. The particle horizon marks the maximum distance from which light could have reached an observer since the beginning of the universe. It defines the boundary of the observable universe at the present time, enclosing all regions that have ever been in causal contact with us. The event horizon, by contrast, marks the maximum distance from which light emitted now will ever be able to reach an observer in the future. In a universe with accelerated expansion, the event horizon lies inside the particle horizon, because regions that are visible today may eventually recede so quickly that their future signals can never arrive. One quiet irony is that the observable universe grows over time as the particle horizon expands, yet the event horizon remains fixed for a given cosmological model, silently setting a permanent limit to what we can ever know. Another irony is that galaxies we see now in their youthful state may one day slip beyond our event horizon so that their light will never again reach us, even as they continue to exist in their own regions of space-time. A third irony lies in the fact that while the universe may be spatially infinite, the observable portion is always finite, bounded by these horizons, leaving the majority of the cosmos forever beyond reach. A lesser-known detail is that the size of the particle horizon depends on the entire expansion history of the universe. In the early radiation-dominated era, it grew more slowly than in the later matter-dominated era, and during acceleration its growth slows again. Calculating the particle horizon requires integrating the inverse of the expansion rate over cosmic time, yielding a present comoving radius of about 46 billion light-years, larger than the simple product of the speed of light and the age of the universe, because space itself has expanded during the journey of the photons we now receive. The event horizon in the case of a cosmological constant-dominated universe has a comoving radius of about 16 billion light-years. This means that light emitted today from a galaxy more distant than this will never reach us no matter how long we wait. These concepts are not merely geometric curiosities, they have practical consequences for what can be measured. Cosmic microwave background photons, for example, come from a shell just inside our particle horizon, representing the most distant electromagnetic signal we can detect. Beyond that, any information must come from messengers that decoupled earlier, such as neutrinos from the cosmic neutrino background, or gravitational waves from the earliest moments, both of which are far more challenging to detect. The existence of an event horizon also means that in the far future the observable universe will contain fewer and fewer galaxies as more cross beyond it. Eventually, only the local group and its merged remnant will remain visible surrounded by darkness, not because the rest has vanished, but because its light can no longer arrive. This gradual isolation is a direct consequence of the accelerating expansion driven by dark energy. The interplay between horizons and cosmic history can be illustrated by considering different expansion scenarios. In a decelerating universe without dark energy, the particle horizon would grow without bound, and there would be no event horizon. In an accelerating universe with a constant dark energy density, the particle horizon continues to grow slowly, but the event horizon approaches a fixed size. If dark energy were to increase with time, the event horizon would shrink, bringing more of the universe beyond reach even sooner. A lesser-known subtlety is that while horizons set ultimate limits, gravitational lensing and other effects can allow us to infer information about structures close to these boundaries indirectly by the way they influence light from nearer sources. However, nothing can carry new information across an event horizon once it has formed for a given observer's world line. The particle horizon also carries implications for the homogeneity of the universe. The near uniformity of the cosmic microwave background across regions that could never have been in causal contact in a simple Big Bang model is known as the horizon problem, one of the motivations for the idea of cosmic inflation. Inflation's rapid expansion would have enlarged a small causally connected region to encompass the entire observable universe, explaining the observed uniformity while allowing for the tiny fluctuations that grew into today's structures. Without such a mechanism, the similarity of distant regions separated by more than a particle horizon's distance at recombination would be difficult to account for. In the context of general relativity, horizons are not physical surfaces, but light-like boundaries in space-time diagrams dependent on the path of light rays and the expansion rate. They are distinct from the event horizons of black holes, though the mathematical analogy is close. Both mark regions from which signals cannot escape to the observer. The difference is that a cosmic event horizon surrounds every observer in an accelerating universe regardless of position, and moves relative to the expanding grid of co-moving coordinates. Understanding horizons also requires careful distinction between different measures of distance in cosmology. Comoving distance factors out. The expansion proper distance measures the instantaneous separation at a given cosmic time, and light travel time gives the time photons have been in flight. These measures can differ greatly for the same pair of events because space itself is dynamic. The particle horizon, for example, has a proper radius today much larger than the product of the age of the universe and the speed of light, because the expansion has lengthened the paths along which photons travelled. The event horizon's proper radius in turn represents a scale beyond which even an infinite weight will not suffice for a photon to arrive. The existence of horizons imposes a fundamental modesty on cosmology. However sophisticated our instruments become, there will always be regions whose current state we can never observe, and events that happen there will remain unknowable. The observable universe is thus both a vast domain and a small patch in a possibly infinite whole. As time passes, the observable region changes in composition and extent. New regions come into view near the particle horizon, while others vanish beyond the event horizon. For now, we live in an era when the observable universe contains hundreds of billions of galaxies, allowing us to map large-scale structure and test cosmological models with precision. In the distant future, the sky will tell a much smaller story, and the full richness of the cosmic web will be preserved only in records made during this relatively brief observationally favourable epoch. The expansion ensures that horizons will continue to shape what we can know, defining not just the edge of sight, but the edge of possibility, a limit written into the fabric of space-time itself. The universe's accelerating expansion alters not only the distances between galaxies, but the very structure of what can remain observable, gradually transforming the cosmic landscape into one of increasing isolation. As the scale factor grows faster, light from more distant regions must cross an ever-expanding gulf to reach us, and for many sources the expansion rate outpaces their ability to send new signals. Galaxies that are currently visible will in the far future slip beyond the event horizon, their last photons arriving in a diminishing trickle before fading entirely from our sky. This is not because they vanish, but because the geometry of space-time prevents their light from ever catching up. One quiet irony is that even as the particle horizon grows, giving us access to regions of space that were once unobservable, the event horizon trims away parts of the cosmos that we can never revisit in any future epoch. Another irony is that the acceleration which enables us to infer the presence of dark energy will over vast timescales remove from view most of the evidence that dark energy exists. A third irony lies in the fact that the universe's largest structures, the filaments and walls of the cosmic web, will eventually be torn from our observable reach, leaving behind only the bound remnants of local matter. A lesser-known detail is that as acceleration proceeds, the recession velocity of distant galaxies in proper coordinates exceeds the speed of light, not because relativity is violated, but because this velocity is the result of the metric expansion of space, which is not limited by the local light speed constraint. Photons from such galaxies can still reach us if they were emitted when the galaxies were closer than the event horizon, but once that boundary is crossed, no further light will arrive. Over the next 100 billion years, the universe will transition from a richly connected network to a sparse island, with the merged remnant of the local group, often called Milkomeda, becoming the dominant visible structure in our sky. Beyond it, the cosmic microwave background will continue to cool and redshift its peak wavelength, stretching into the meter range, then the kilometer range, eventually becoming undetectable by any conceivable receiver. The fading of the microwave background is more than a loss of a landmark. It removes the earliest direct evidence of the hot Big Bang, leaving future astronomers without the observational pillars that support today's cosmological model, without galaxies beyond the local gravitationally bound group, and without the background glow, the reconstruction of the universe's expansion history will be far more difficult for any future civilization. The isolation caused by accelerated expansion is not instantaneous but gradual, with measurable effects even on the timescales of current cosmology. The redshift of distant galaxies increases with time, their light dimming, as both distance and wavelength grow. For sources near the event horizon, the rate of redshift growth is rapid. The spectrum slides toward longer wavelengths at an accelerating pace, and the arrival rate of photons slows, producing an exponential fading. This dynamic horizon behavior is a direct outcome of the Friedmann equations with a dominant cosmological constant, and it represents a steady reshaping of the observable universe's boundaries. The suppression of large-scale structure growth in the accelerating era is another consequence of this shift. Once dark energy dominates, gravitational collapse on the larger scales is effectively frozen, and the pattern of filaments and clusters becomes fixed in co-moving coordinates. Smaller-scale processes such as star formation, galaxy mergers, and black hole accretion continue within bound structures, but the cosmic web as a whole stops evolving in form. Over time, even the bound structures will exhaust their gas supplies, quenching star formation, and leaving only stellar remnants, planets, and black holes. A lesser-known implication is that accelerated expansion also influences the trajectories of intergalactic material ejected by galaxies. Streams of gas and stars flung outward by gravitational encounters or energetic events may never reach neighboring systems if the expansion stretches the intervening space faster than the material can traverse it. This makes the future universe a place not only of observational isolation, but of physical separation on scales that are currently traversable. The event horizon's fixed proper radius in a cosmological constant-dominated universe sets an upper bound on the maximum separation over which two unbound objects can exchange signals. This bound shapes not only the fate of light, but also the fate of any material or information attempting to cross intergalactic space. For civilizations, if they were to exist, this would represent an ultimate limit to intergalactic exploration and communication, one imposed not by technology, but by the nature of space-time itself. The irony here is that the same equations that reveal the possibility of expansion without bound also impose a strict bound on causal connection. Observationally, we're in a privileged position in cosmic history, the era when dark energy is just beginning to dominate, when the sky is still filled with billions of galaxies, and when the microwave background remains a bright, measurable signal. This window is brief on cosmological timescales, perhaps only a few billion years wide before the majority of galaxies are swept beyond the event horizon. In that sense, cosmology is a discipline whose richest phase coincides with our current epoch, not because the universe is more interesting now, but because it is more accessible. This accessibility has allowed the convergence of multiple lines of evidence: supernova distances, baryon acoustic oscillations, weak lensing galaxy clustering, and the cosmic microwave background into a single coherent picture. In the far future, that picture will be harder to reconstruct. The gradual disappearance of distant galaxies also has implications for the cosmic energy budget. As light from beyond the event horizon ceases to arrive, the total energy density and radiation within the observable universe decreases more rapidly than from redshift alone, further emphasizing the dominance of dark energy in the local balance. Meanwhile, the matter density inside the horizon remains constant in comoving terms, but dwindles in proper density as the volume increases. Eventually, dark energy will account for effectively all of the energy within the observable region, not because its absolute density has increased, but because everything else has diluted or receded away. The boundaries of what can be known are thus determined both by the particle horizon, which records the past, and by the event horizon, which restricts the future. The interplay of these horizons defines a shrinking intersection of space and time in which information can be exchanged. Our moment in that overlap is expansive but temporary. The acceleration that shapes it is not a burst, but a steady, unrelenting feature of the universe's late-time evolution, one that will continue as long as dark energy behaves like a cosmological constant. In such a future, the night sky becomes less a map of distant places and more a record of the local environment, the grandeur of the cosmic web replaced by the close company of a few bound galaxies. Yet the physics that leads to this isolation is the same physics that allows us now to measure and understand the expansion, and to know, however briefly in cosmic terms, the immensity of the universe that lies beyond our immediate reach. In the deep future, when the accelerated expansion has carried almost all galaxies beyond the event horizon, the universe within sight will be quiet and sparse. The merged remnant of the local group will contain stars of many ages, but over tens to hundreds of billions of years, the bright, short-lived ones will disappear, leaving cooler, dimmer stars to dominate the light. Over still longer spans, even these will exhaust their fuel, becoming white dwarfs that slowly cool toward blackness. The interstellar medium will grow thin as gas is locked away in stellar remnants, and new star formation will dwindle to nothing. The cosmic microwave background, once the brightest signal in the universe, will have been redshifted to wavelengths so long that it is undetectable by any conceivable technology, its energy spread over volumes so vast that it merges with the general faintness of the vacuum. One quiet irony is that the early universe, when matter and radiation were intertwined in a dense plasma, was both hotter and more uniform than the cold, clumped landscape of the far future. Another irony is that the same acceleration that limits our cosmic view also ensures that the local environment remains gravitationally bound, preserving a small island of structure in an ocean that recedes forever. A third irony is that the processes of stellar birth and death, once common across billions of galaxies, will continue only in miniature within the remnants of a single galactic conglomerate, their light shining into an emptier and emptier sky. A lesser-known detail of this era is that stellar remnants will occasionally collide or merge, producing brief bursts of light or gravitational waves that momentarily punctuate the cosmic quiet. Binary white dwarfs can spiral together through gravitational wave emission, igniting as type Ia supernovae even after star formation has long ceased. Neutron stars, if present, may merge to produce heavy elements and short gamma-ray bursts. Such events will become rarer as time passes, but they will remain as occasional reminders of the energetic processes that once shaped galaxies. The large-scale structure of the universe will by then be frozen in moving coordinates, with no new filaments or clusters forming beyond the local bound region. Black holes, both stellar mass and supermassive, will persist, slowly gaining mass from the capture of stars and gas until such sources are depleted. On timescales trillions of years into the future, black holes themselves will evaporate through Hawking radiation, though the process is so slow for massive black holes that it dwarfs the current age of the universe by many orders of magnitude. The accelerating expansion means that even if observers existed in that remote epoch, they would see only their own bound system, and perhaps faint traces of radiation from decaying black holes in the farthest reaches of their environment. Without the cosmic microwave background, without the Hubble-Lemaitre law visible in the recession of galaxies, and without baryon acoustic oscillations imprinted on a broad distribution of galaxies, reconstructing the true scale and history of the universe would be almost impossible from local evidence alone. The universe would seem static, timeless, and limited its expansion, hidden by the very acceleration that once made it so apparent. A lesser-known implication of this is that our current ability to do cosmology on a universal scale is temporary, tied to an observational window that will not last. The far future sky will be dominated by the slow motions of stars within the local bound group, their orbits determined by the combined gravitational pull of all the merged galaxies. Outside this island, the expansion will have stretched all light to invisibility. The event horizon will still exist, defining the outermost reach of causal influence, but nothing beyond it will send new light or signals inward. The particle horizon, though larger than it is today, will be irrelevant to observation, as most of the regions it encompasses will be long past the possibility of communication. In this late era, the cosmological constant will continue to dominate the energy content of the universe, maintaining the accelerated expansion indefinitely. the energy density of matter and radiation will approach zero in proper coordinates, while the vacuum energy remains constant, ensuring that the geometry stays in a de Sitter-like state. The thermodynamic evolution of such a universe leads toward a state of maximum entropy, sometimes called heat death, in which no free energy remains to do work and all processes proceed with infinite slowness. This outcome is not a dramatic end, but a gradual fading, a transformation of the cosmos into a cold, dilute, and unchanging expanse. The irony is that the same physics that gave rise to stars' galaxies and the richness of the cosmic web also leads to this near emptiness and end point, as much a consequence of general relativity and quantum field theory as the vibrant early stages were. If dark energy is truly constant, this is the most likely fate. If it evolves in time, other possibilities exist, but no current observation points clearly toward them. The far future will be shaped by the parameters we measure today, frozen into a trajectory that can be calculated with confidence if the standard model holds. In such a universe, the memory of expansion, the clues from the cosmic microwave background, and the evidence from large-scale structure will be gone erased not by destruction, but by inaccessibility. The cosmos will continue, but the story it tells will be shorter for those who listen in that time. A lesser-known perspective is that even in such an apparently static future, quantum processes will continue on microscopic scales, and the occasional rare event such as particle decay or black hole evaporation will release energy into the cold. Over unimaginable spans, these will be the only changes in the universe otherwise defined by its stability. The present era, rich in accessible information, will be seen in retrospect, if it can be seen at all, as a fleeting phase of discovery. Our ability to know the size, age, composition, and fate of the universe is a product of living when the sky is still full of distant light and ancient echoes. The expansion that carries galaxies away from us will continue without pause. The event horizon will remain the unseen edge of future possibility, and the local island of matter will drift through the long night as the rest of the cosmos recedes beyond recall. In this way, the answer to why the universe keeps expanding is also an answer to why its visible story will eventually contract, leaving only a remnant sky and the memory preserved now of the vastness that once was.